Viewpoint-driven formation control of airships for cooperative target tracking. Subject relative formations are used to keep line of sight on a subject from different angles simultaneously. This is crucial for aerial motion capture. In previous work we have shown that for mocap the following two main formation conditions are necessary. First, mocap accuracy decreases when the UAVs are too far, thus a threshold distance to the subject is needed to maintain accuracy while ensuring subject safety. Second, the UAVs need to maintain specific relative angles with respect to the subject, which depends on the number of UAVs in formation. With multicopters, every UAV can independently point its camera towards the subject, while the formation follows the subject and maintains distance and angular separation. However, multicopters are noisy and can frighten some subjects, such as wild animals we would like to study. Also, due to inefficient propulsive lift, they suffer from short flight times. For such applications, our idea is to use buoyant, lighter-than-air vehicles, airships. However, airships cannot move independently of their own orientation. For these vehicles, we need a different formation strategy. Our solution is to mount the camera sideways and then orbit the subject. Airships must stay in motion to remain maneuverable. If the subject is stationary, this is the only way we can maintain distance and separation between airships. When the subject is moving, or there is wind causing the airships to drift relative to the subject, orbiting is still possible, but with varying radius. By maintaining a constant angular velocity, we can maintain constant intervehicle separation. We speed up or slow down to compensate for the subject's motion when we are oriented parallel to the subject. But when oriented perpendicular, we cannot compensate the subject's motion vector. This causes periodic changes in orbit radius. To maintain angular velocity at the larger radius, we need to further accelerate. This adds up to a velocity increase of 2 times the subject velocity at the furthest point, and a velocity decrease 2 times the subject velocity at the closest point. Orbiting is always possible if combined wind and subject velocity do not exceed 1/4 of the airship velocity range. The difference between minimum speed required to remain maneuverable and the maximum speed the airships are physically capable. In 3D and with downward angled cameras, the airship flight altitude also must change with changing radius. This shifts the camera angle forward or backwards as the airship pitches up or down. The bank angle is not constant either. It depends on the aerodynamic forces and gravity. Motion and orientation are tightly coupled in 3 dimensions. We capture this behavior in a motion model that takes airship flight physics and constraints into account. We solve for an optimal 3D trajectory by minimizing a coast function. It increases with the distance of the subject to the center of the camera frame, and also with the angular separation error between airships. We also penalize flying too close or too far. Based on this, we designed a model predictive formation controller, which computes optimal control solutions in real time. This visualization shows 3 airships orbiting a subject at the center. The arced lines are the predicted trajectories over a fixed time horizon. We integrate this in our cooperative visual tracking framework, AirCap, designed for aerial motion capture, and track a person with the formation of simulated airships. We utilize our flight physics simulation for non-rigid airships and low-level vehicle control from our previous work. The far left displays simulated camera views and visual detections for 3 airships. The center visualizes the predicted MPC trajectories. The right shows the entire formation in the simulated world. Using this simulation, we ran experiments to evaluate our MPC. We test its limits by changing parameters such as wind and subject motion. We demonstrate the formation control algorithm on our real airship in an outdoor experiment. In this video, we see our airship from the perspective of the subject on the ground. The airship estimates wind and adjusts the trajectory accordingly. The MPC formulation can easily be extended for different applications. For this demo, we added static obstacles and collision avoidance constraints. You can find our code, demo, and instructions for reproduction on our GitHub page, github.com/robotperceptiongroup/airshippmpc. Thank you for your attention.